Here's a continuation of that 3D shaft problem from class 16, right? And I didn't originally plan to have this in the class, but I wanted to get the design aspect back. We want to get to it sooner than waiting towards the end of the semester where we have the shaft project, which is similar to what we're doing here. We want to redesign, but we're going to do it with static design. Eventually, we're going to do a fatigue design, but here we need to design it for static loading. So let's say that we want to redesign this, and we're going to pick, because we have some code or some standard, that we're going to use 1.5 as our design factor. How would we go about doing that with maximum shear stress theory or distortion energy theory? Well, first off, we create a max allowable shear stress or a max allowable von Mises stress, and we're going to set the equation for that stress to that allowable stress and then work out backwards. Well, how are we going to work out backwards? Well, we know that the bending stress with a stress concentration is this KT times MC over I. We can put in that C is D divided by 2, and the moment of inertia is pi over 64 times D to the fourth. And a couple things cancel out, and we get some numbers. So we may have already run across in a couple examples in Shigley, for a circular shaft, this is bending stress, right? And then also for shear, a similar thing. Now we're going to have that KTS because it's the shear stress concentration times T over J. And we plug in what R is and what J is, and we get now 16T over pi D cubed. All right, so we're going to use those together. And here is like a summary of a redesign with maximum shear stress theory. So here are the equations that I just mentioned up above that we're going to use. So we start out with setting that the allowable to the, which is the strength divided by 2 divided by the design factor. Set that equal to our absolute maximum formula. It's simplified because we know it's uniaxial stress is what's going to end up with there, so we can use that. And then plug in our bending stress and our torsion right there, right? So we stuck them in, and we can pull out a 16 divided by pi and D cubed. Now, one of the reasons why I could do that is because we have it squared and square rooted, right? So that's a common factor, and also that 32 got divided by 2 right there, so that turned it into 16. So that's a little convenient. And then we can flip this thing on its ear and solve for the diameter. So here is a generic equation. You might want to write this down somewhere. This is, because I did the algebra for you. So plug in the values that we know. We know what the moment is, and so forth. We know the torque. So we have all of these are knowns, right? And since we have the design factor, we can put all these in there. And I get that I need 67.83 millimeters. Well, this is based on maximum shear stress theory. We could do it as well with distortion energy theory, right? So we just use these equations instead. We just change the allowable and go for the von Mises and plug them in there. Now, kind of a little bit of a different thing happens. We didn't have that divided by 2. So in order to get that address that 32 and the 16 in common, we pull a 16 out and we put a 4 right here. Now you'll see this in some equations, especially in chapter 7. You'll see this in a place so just look at the algebra and see that you confirm it that that's be true. But now that we have this, we've moved this D cubed to the outside right here. We can solve for it. So it's a very similar equation, and the outcome isn't that much different. I still get right around 67 millimeters, and so we use the next size up, which would be 70 millimeters. That's our design conclusion, that 70 millimeters is a good one to use, including with the stress concentration. Let's see, do I have anything more? No. Okay, so let's take a look at what we would do with in Excel, right? So I made this spreadsheet up here, And first off, no, we'll leave it the way it is. You can see that we got for the for this. This is what we had from the previous analysis, where with the stress concentrations and everything. What's really useful when you set something up like this is you could go to data up at the top, and then to what if. It's got a pull down, and one of the choices, there's only 3 choices, is goal seek. Very useful for design, because we have this set up, and we want to double check our spreadsheet is correct, and we're pretty confident because we did it by hand calculations and they match. We hit goal seek here, and it's this little tiny interface, and it's so you want to, here I'll put it right over my face so you can see it. So it's very intuitive. Set cell. So I want to set one of my safety factor cells. So I'm going to try maximum shear stress theory first. Set the maximum shear stress theory cell, boom, right? Set it to 1.5, right? That's our safety factor we want, by changing the diameter up here. So I'm changing that diameter, and now we're going to hit OK and watch it. It's going to spin a little bit. Oh, it spun a little bit. You didn't quite see it. It went really fast. But it made the target. It got the target. It made that into 1.5, right? And what is the answer? Well, look at that. It's 0.06783. It's the same thing as we had. Get it up here. Up, boom, right there. 6783. And I didn't just write this one down, and that is the correct one. And then we could do the same thing up here. Go to the what if analysis and the goal seek, and this time let's set the distortion energy theory to 1.5. And maybe we can see this because it's not going to be obscured by my ugly mug. And we hit OK, boom, and it went really fast. And we got right there. We got 0.0673, right? So boom. So we got 67.3. And we could do all this. Let's try this out with trying for. Let's set these to 1, and so we're gonna let's pick this as 0.07 right there, right? So we're going to predict that our maximum von Mises is 145.7 if we have a 7. And notably, we got rid of the stress concentrations, right? So it's going to be greatly reduced. So we're going to look for, if we have 70 millimeters without stress concentration, I'm going to predict 145.5. And I'm going to use this guy right here. So all we need to do is come up, the way that I set this thing up, I built them so that all of the sketches that I made were, from each spot along here, were all dependent on the first sketch. So we can make that 70 right here, and it will hopefully cascade all the way through. There you go. There's that thing. So it made it 7. This whole thing is 70. So now all I need to do is I can hit the mesh and run. That's the lazy man's way to solve the thing, right? And it's running, hopefully. I think it's running. There it is. It's solving it. And it's solving it. What did I do? Make the thing too tight? No, there you go. 143.4. 145.5. We are now design engineers. Of course, the scale doesn't really isn't all that exciting because it's up to 300. But if I was going to make this in the same report, I would use the same scale before as now, right? Because or use in real bold and say that we redid the scale, right? They're going to make it very clear that you used a different scale if you're going to put 2 color plots of the same thing near each other. So anyway, that's redesign, right? You did it a couple different ways. We could actually make this in SolidWorks. I haven't done it in a while. We could make this some adaptive thing, right? So we could set what the maximum we wanted or some other measure and then have the diameter change, and it could actually figure out what that would need to be. But we could also do it by hand in a simple problem like this. But there it is. You're a design engineer now. So the equations that you want to recall, this guy right here, pretty good one to know for maximum shear stress theory. This one's a pretty good one for distortion energy theory in this simple design type of problem. 10 minutes, not so bad.